This lecture shortly introduces new system architecture paradigms relevant in IoT context. Today, IoT systems have transited from being perceived as sensor networks to smart networked systems capable of solving complex tasks in mass production, public safety, logistics, medicine, and other domains, which require a broader understanding and acceptance of current technological advancements. Since the very beginning of sensor networks, one of the main challenges have been data transport and data processing, where significant efforts have been put by the ICT community towards service-based systems architectures. The current trend, however, already provides considerable computing power available even in small mobile devices, and therefore the concepts of future IoT already are shifted towards smarter and more accessible IoT devices. Main current trends are cloud computing, fog computing, and cognitive IoT systems. Cloud-based computing is rather well-known and widely employed paradigm, where IoT devices can interact with remotely shared resources, such as data storages, data processing, data mining, and other services that are not available to the system due to cost effectiveness or other limitations. Although the cloud computing paradigm can handle vast amounts of data from IoT clusters, the transfer of extensive data to and from cloud computers presents a challenge due to limited bandwidth. Consequently, there is a need to process data near data source, employing the increasing number of smarter devices with large processing power and an increased number of service providers available for IoT systems as well. Some sources refer to shared computing as edge computing, where significant part of the data computation is done on the mobile device, while the large batches or other demanding tasks done on the cloud services. Fog computing addresses the bottlenecks of cloud computing regarding data transport while providing the needed services to IoT systems. It is a novel trend in computing that aims to process the data near the data source. Fog computing pushes applications, services, data, computing power, and decision making away from the centralized nodes to the logical extremes of a network. Fog computing significantly decreases the volume that must be moved between end devices and the cloud. Fog computing enables data analytics and knowledge generation to occur at the data source. Furthermore, the dense geographic distribution of the fog helps to attain better localized accuracy for many applications as compared to cloud. Cognitive IoT, besides a proper combination of hardware, sensors, and data transport, comprises cognitive computation, which consists of the following main components. Understanding. In case of IoT, it means systems' capability to process a significant amount of structured and unstructured data, extracting the meaning of the data, produce a model that binds data to reality. Reasoning involves decision-making according to the understood model and acquired data. Learning, a creation of new knowledge from the existing sensed data and elaborated models. All three approaches, from cloud to cognitive systems, are focusing on adding value to IoT devices, system users, and related systems on demand. Since market and technology acceptance of mobile devices is still growing, an amount of produced data of those devices is growing exponentially, mobility as phenomena is one of the main driving forces of the technological advancements of the near future.